welcome to my talk. Today I'll be talking a bit about how a mass point moves on a donut, and you'll get at least a partial answer today. Some of you might have noticed that maybe the title of the talk is a bit different. That's due to the fact that the talk that I had before was too much for 45 minutes. So yesterday, basically, I worked the whole day to change it to this. So in order to sort of find out, in order to find out how a mass point sort of moves and behaves on a torus or a donut, as it is known colloquially, we'll be using Noether's theorem, which goes as following. If the Lagrangian system admits the one-parameter group of diffeomorphisms, then the Lagrangian L has a conserved quantity I, and in local coordinates on M, I is written in the following form. So obviously, in order to sort of understand what this theorem is trying to tell us, what we first need to find out is what all these terms mean. So what is a manifold? What is a Lagrangian? What is a one-parameter group of diffeomorphisms? So in the following, this is sort of going to be the structure of the talk. We're going to go through the individual terms that come up in the theorem that we're trying to use to sort of classify the movement of a mass point on the torus. And we'll be starting off with what a manifold is. So what is a manifold? The definition that I give is that an m-dimensional manifold is basically a set M together with a collection of charts that cover this manifold M, and this collection of charts that cover M is called an atlas. So what is a chart? A chart is an open set U of Rm together with a one-to-one mapping phi of U onto some subset of M. So the image of U under this function phi is contained on the manifold M. So how you can imagine this is basically we have the manifold we have the manifold up here, and we have the different charts on the level of Rm, sort of giving us local coordinates on the manifold M. And we also have some further conditions on how these charts sort of behave with each other. So if two charts U and U prime intersect in their image on the manifold M, then we require that the mapping on the intersection is smooth. So you can sort of view this as a coordinate transformation. So here we're basically using local coordinates to describe this point on M, and here we're using local coordinates to describe these points on M, and basically on their intersection we require the coordinate transformation to be smooth, so well behaved in some manner. And one thing that I haven't written on here, but which is always there implicitly in the background, is that we have some sort of Hausdorff condition on M, so 2 points can sort of be separated on M. Okay, so since we're trying to look at the movement of a particle on a torus, the torus better be a manifold. And in fact it is. It's a two-dimensional manifold. And we can sort of parameterize any point on the manifold by a pair of angular coordinates in the following manner. So how I want you to view the torus is sort of as a surface of revolution. And if we have the torus in three-dimensional space, basically we can parameterize the normal Cartesian coordinates, if you will, through the following formula. And you might be wondering, okay, how do I come up with this formula? So basically what happens is I have a circle which is centered in A in this plane, in the XZ plane, and then I rotate it with this matrix around the Z-axis with 2 pi. And then I come up with the torus. And the sort of charts which give us the atlas that covers and describes the torus fully can, for instance, be given by these two open subsets of R2. Okay. So since we want to describe the movement of a particle on the torus, on the manifold, we want to sort of get some sort of intuition behind what a curve looks like on a manifold, how we can describe it. So basically what we can do is we can describe a curve on the manifold with local coordinates. So on the level of the charts, basically we have some sort of curve, and under the function phi, we're then describing the curve on the manifold M. And then basically the curve, if it's this I interval is a subset of R, takes on the local sort of form that is given here. And if we're looking at the derivative of the curve on the manifold, so if we take the derivative at this point x, then we call this the tangent vector. And again, in local coordinates, it has the following form. And what you can sort of imagine these del xi's to be is sort of placeholders or special bases. It's basically a directional derivative. So in which direction can the derivative go on the manifold M? And we can sort of generalize this concept of curves passing through a point x on the manifold M with the tangent space. So basically, if we look at the collection of all curves on the manifold M, which are smooth and pass through point x, if we take the derivatives, this spans the tangent space. And these placeholders, or the special bases that I was talking about before, sort of form the basis of the tangent space at this given point expressed in local coordinates. And how you can imagine this is naturally sort of the point x on M is the origin point, and we add the tangent vectors, or the directional derivatives, like you would in a normal Euclidean space, whereas here x is the origin and not 0. Okay, and since we're looking at the torus again, it's a two-dimensional manifold, remember, so the tangent space is also two-dimensional at any point x on the manifold itself. And how you can basically imagine this is on the level of charts, we're basically looking at the directional derivatives and we map it onto the manifold itself. And here you can sort of see the construction. We look at a point x, we look at some smooth curve on the manifold, and then we take its directional derivative, and these sort of span the tangent space at that point. Okay, so now that we have maybe some more clear picture of what a manifold is and what a curve looks like on a manifold, we want to get into what a one-parameter group of diffeomorphisms actually is. And basically, the definition that I'll be using is that a one-parameter group of diffeomorphisms, denoted like this. So for each S and R, we have a diffeomorphism. It's basically induced by the group R with addition acting on a manifold M. So what do I mean by this? Basically, we have a smooth map, psi, such that we have this property. It's often referred to the associativity property. Furthermore, the manifold M is sort of invariant under the neutral element with regards to the addition. This is called neutrality. And here, this is sort of the invertibility condition where the diffeomorphism comes into play. So if we fix a S in R, then we can sort of invert and go back to the point X in M. And this is sort of where the term diffeomorphism comes into play. So to give you an example, I'll be looking at the irrational flow on the torus, and what this is basically a curve on the manifold T2, which is the torus, and on the coordinate level, basically it's like a curve with the slope omega, where omega is a real number. And if you map this under the parameterization that I gave for the torus, then the image of this curve looks like this. And with this, we can sort of define a global group action with sort of us acting on each point x on the torus. And what we do is we sort of have the irrational flow starting at each point x and m. So this would be the orbit, as we call it, for one point x and m. And we sort of start the irrational flow at each point x and m. And this defines us a group action, or if you fix a S, sort of a diffeomorphism on the manifold, in this case being the torus. Okay, so now I want to get into what a Lagrangian system of equations is. And for the sake of this talk, I will not go into the technical details and the things that are sort of in quotation marks, you can interpret as there being sort of more stuff that one needs to discuss. So in the following, we will be interested in the extremals of functions phi defined on a space of curves, and functions of this form we're going to call functionals. And basically how you can interpret extremal is extremal of a functional is a curve such that the derivative of phi evaluated at gamma is 0 in all directions. So you can sort of think of it as if you're taking a normal function of a real variable, then it's sort of a stationary point. So in whichever direction you go, the derivative is 0. And in particular, the functional that we are going to be looking at will be of the form that I give here. And basically, L will be sort of a smooth function on the torus, which will represent the energy. And it will depend on basically the location and the derivative in some sense, given in local coordinates on the manifold, which in this case is the torus. Okay, and in order to sort of find and classify extremals on the torus, what we need to do is, this will be quite an important equation. It's called the Euler-Lagrange Equation, and that's also sort of how the name Lagrangian formalism comes into play. So basically, if we have this equation, this is called the Euler-Lagrange Equation for the functional that we are interested in. And we have this following theorem that a curve gamma is an extremal of the functional that we're interested in on a space of curves joining 2 points in A and B, if and only if the Euler-Lagrange equation is satisfied along gamma, which means that if gamma fulfills this equation, then it is an extremal of the functional we're interested in. And we can sort of generalize this concept of the Euler-Lagrange equations sort of delineating what a extremal is by the following sort of theorem. Since we're sort of maybe looking at the movement of a mass point on the torus, we're looking at a physical system in some sense. And if we're looking at a mechanical system obeying Newton's equations of motions, in this case we have some sort of conservative force field acting on a collection of mass points in the system, then the motions of these mass points coincide with the extremals of the functional of the following form, where L is the difference between the kinetic energy and the potential in the system. And you can check this with just setting basically the potential and the kinetic energy to be of this form, and then you directly get the Euler-Lagrange equations out here. Okay, so as I mentioned before, what we're interested in is motions of a mass point on the torus. So how you can basically imagine a torus coming up in a natural system is if you have a force field which really is strong and is pointing towards the torus, or the donut, if you will, then the particle or the mass point is sort of forced to move along the torus. And you can sort of imagine this as being the physical system. And what we're interested in is going to be the kinetic energy of a mass point on the torus. And we sort of forget about the force field since we're sort of forced to move on the torus itself. And in literature, you'll find that this is called a natural system. So we're looking at systems of the form T minus U, with T being the kinetic energy and U being the potential. Okay, so what does Noether's theorem tell me about the motion of a mass point on the torus? So I remind you, the theorem goes as following. If the system, the Lagrangian system, admits the one-parameter group of diffeomorphisms, I haven't mentioned what admits means. Basically, admits means if you have a diffeomorphism psi of s, then the form of the Lagrangian doesn't change under this sort of coordinate transformation. So if we apply psi of s to L and look at it in different coordinates, the form of L will still be the same. And this is what it means that the Lagrangian system admits the one-parameter group of diffeomorphisms. And then the theorem goes as following. Then the Lagrangian L has a conserved quantity I, and in local coordinates x on the manifold M, the conserved quantity is of the following form. And sort of how you can think of this is that the conserved quantity is sort of the change of the function L that we're trying to maximize or minimize with respect to the velocity vector multiplied with how quickly the coordinates change on the manifold itself. Okay, so just to remind you, this is the parameterization that we're using on the manifold being the torus. And these were the charts or the atlas that covered the torus. And what we're now trying to do is with Noether's theorem, we're trying to sort of gain some information about how a mass point moves on the torus itself. So the Lagrangian, if we have it in the normal Cartesian coordinates, looks like this. And then if we sort of calculate it with the parameterization that we're using, we then get this form. And we also notice that basically the Lagrangian doesn't depend on rho. So the second coordinate doesn't come up in the Lagrangian or the function that we're trying to minimize or maximize, which means that we can define a one-parameter group of transformations of diffeomorphisms that leave Lagrangian invariant. Since it doesn't depend on rho, if we sort of shift rho by some sort of factor, this will not affect the function L itself. And how we do this is basically we define the group action of R with addition on the torus by following form. We just shift in the parameter rho. And I'm taking mod 2 pi here because if you remember here, we have sort of 2 pi periodic functions flying around. Okay, so this is sort of how the group action would look like. These are the orbits. We're basically shifting in the rho parameters, so we're just going around the torus in these sorts of orbits. Okay, so what Noether's theorem is then telling us is that the following quantity is preserved. And if we sort of change this to cylindrical coordinates, what this is just the angular momentum in the z direction. And you can sort of notice that the conserved quantity that we get from Noether's theorem is sort of in direct relation with the symmetry of the torus with respect to the z-axis, because the torus sort of looks the same if we go around the z-axis. And in this sense, the conserved quantity also has to do with the symmetry of the torus itself. Okay, so now we want to gain maybe a bit more information on how a mass point will move, given that we have this conserved quantity on the torus itself. And as I said, we'll be switching to sort of cylindrical coordinates, which is basically polar coordinates with a z-axis added to it, because it makes the discussion slightly easier. So then the conserved quantity that we just got from Noether's theorem takes on the following form. And here, sort of gamma is this curve, and we're looking at the mass point as it sort of cuts this blue circle, if you will. And here V represents the velocity vector of the point, and alpha is sort of the angle between the velocity vector and this blue circle when the point is intersecting this big blue circle. And since we're sort of in a conservative force field, as you can remember, we're looking at a natural system. We know by sort of the law of conservation of energy that the velocity itself will not change. So we know sort of this quantity will be the same. So with the information that this is a conserved quantity, so is a constant, then we sort of get this relationship out, which is r times cosine alpha is a constant. And basically, r is the distance from the rotation axis, and alpha, as I mentioned, is this sort of angle between the blue circle where the mass point sort of intersects, we get out that this is a constant. So if I move up here, the radius or the distance to the rotational axis decreases, so I know that the angle here will sort of also decrease in some sense. And actually, in differential geometry, this is known as Clairaut's theorem. So basically, this sort of coincides with curves on a manifold M, which in some sense have minimal distance, minimal length. And what we were trying to minimize was the energy function, L, which is energy. So in some sense, there's a close relationship between energy and the length of a curve on a manifold M. And okay, as I mentioned, basically I had to change my whole talk yesterday. So I will give you some further reading in case you're interested in the movement of a mass point on the torus. This first article is really a self-contained article, so the only thing that you need to have visited is analysis 2 or some form of it. And basically, this discusses the geodesiacs, the curves of minimal length that I was sort of talking about here, but just from an analysis point of view. And it's really self-contained. It's really nice because they get out a characterization for the different sort of forms that a geodesiac or the sort of curve of a point mass on the torus can take. With the sort of same argument with Clairaut's theorem and something called the critical angle. So in case you're interested in how a mass point moves and what curves it can and cannot take, then I can really recommend this article. It's only 11 pages long, and it's very self-contained, so anybody from the second semester on can read this. Another more sort of challenging article, if you're interested in the movements of particles on the torus and more generally surfaces of revolution. As you saw, sort of the torus comes about by rotating a circle. We can do this more generally by rotating a curve around axis of rotation. This discusses the movement of particles or mass points, if you will, on these sorts of surfaces, and it also gives you some sort of more physically motivated problems when it comes to this. Yes, so these are the references that I used to prepare the talk. And thank you for your time. And yeah, in case any of you have questions regarding leaf formalism or something like this, we can discuss it in the apro. As I said, I'm sorry, but I changed the sort of talk idea. Yeah. Any questions? Yes, Philemon. Yes. Yes. Okay, so basically, there, as I mentioned before, there's a one-to-one sort of correlation between movements of particles that minimize the energy function and movements of particles that minimize the sort of length function, if you will. So in some sense, a geodesiac is a curve which minimizes length. And on the torus, there are sort of 2 or 3 types of geodesiacs. Or curves that a mass point can take. So notice that like one form of a geodesiac could, for instance, just be the meridian. So if I'm going around in a circle here and I sort of don't change this angle alpha or I go proportionally with r. So a geodesiac would, for instance, be a meridian. Then the second type of geodesiac that one can look at is these great circles. So this blue line is the great circle, and this is actually one of the two geodesiacs which goes sort of in the lengthwise direction. The other one would be the inner circle that we have here. And any other geodesiac, any other movement of a particle on a torus actually has to cross this great circle, this blue circle, which is sort of based on the uniqueness of solutions to differential equations. So basically, there are different types of geodesiacs, but a lot of them actually have to pass this blue circle. Does that sort of answer your question or motivate it, maybe?
What's surprising to me is that these geodesics should be able to lift them to like R2, for instance. Right? They would be, I guess, also length minimizing in R2, which means there would be lines, and then when you project into the torus, I'm surprised that.
Yeah, but sort of on the level, yes, this is something called parallel transport if we're on the plane of R2. But when we sort of map it under something that is like non-linear in some sense, right, this curves in a different way. So also if we have some sort of quotient map, right, if it looks straight on the level of R2, the sort of velocity vector that we are transporting along the curve on the level of R2, for instance, will be in a different position if we map it under the chart that we have. So yes, the intuition would be behind like length minimizing. Yes, okay, it's a line on the level of R2, but when we're on the level of manifolds, sort of because the functions that parameterize the manifold are nonlinear, sort of like using cosine and so on. Okay, I would have to think about that. Yeah, exactly, absolutely. But thank you for the question. That's a good question. Does anybody else have a question regarding? Yes, hi.
Yeah, so for these movements,
yes.
you discussed before that the movement is also described by the Newtonian mechanical equations.
Yes, yes.
And you talked about the potential energy.
Yeah.
I was wondering how this potential looks like, because maybe I.
So okay. Basically, what you can imagine this potential to be is usually we have some sort of potential on the torus, and then if we move like upwards or away from the torus, then there's a force field sort of acting very strongly, pointing towards the torus. So, if you will, sort of the potential energy goes to infinity if we go away from the torus, and that's why the point mass is sort of forced to be on the torus. This is an idealized system, obviously, but as I said, this idealization is something called holonomic constraints, comes up in a lot of sort of physical systems, and this idealization is a quite good approximation of physical systems. So as you can imagine, it is basically the potential goes off to infinity if we go away from the torus, so sort of the point is forced to be on the torus itself.
Okay, so there's no potential force, like no difference in potential if you stick to the torus.
Yeah, basically, you can sort of forget, so to speak, about the potential. Yeah. Thank you for your question. Yeah.
You might not have an answer to this, but do you know whether like these kinds of like models are used, for instance, in like tokamaks when we're like trying to because you have a constrained plasma inside the torus, or does like do these models break down with like high energy or high speed?
What do you mean by model? Like, which model are we talking about?
Well, the fact that you said you can model like when using a Newtonian laws of motion, this corresponds to like an actual like physical situation.
Yes. Okay. Wow. Honestly, I don't know under such sort of special physical systems what happens if we can still use this idealization, but yeah, I would have to think about it. If you want, you can write me email. I can research it a bit. Yeah. Thank you. Any other questions?
But wait, you said that the potential outside of the torus is infinite, right?
Yes.
I mean, then it shouldn't matter how high the kinetic energy is, right? I mean, it can break down if the potential is infinite. I mean, if it's not infinite, if it's finite, then sure, there has to be some kind of kinetic energy where it can escape from the torus, but it sounds like that should be possible. But maybe there's some more intricate physics behind that. I don't know.
Yeah, I mean, I think you make a good point. But again, I don't really know these sorts of physical systems, so I would have to look it up. Okay, any other questions? Or are you guys ready for the apéro? Okay, well, in case you have any other questions, please feel free to come to me to the apéro. And other than that, enjoy the apéro. Thank you for coming to today's talk, guys.